Now we have to determine the magnetic force, the magnitude of the magnetic force on these wires. So we know, as we've said earlier, that the magnetic field generated by a wire, a long wire, by Ampere's law is given as the product of the permeability of free space and the current of that wire divided by 2 pi times the distance to the point at which we are evaluating. So to find the magnetic force, or the magnitude of the magnetic force on wire 2 due to wire 1, we're going to evaluate the magnitude of the integral from 0 to L times I2, that's the current in wire 2, and then we're going to take the magnitude of the cross product between the displacement differential and the magnetic field of wire 1. That's just from the version of the cross product that says when you evaluate the magnitude of the cross product between two vectors, it's equal to the product of the magnitudes of each vector times the sine of the angle between them. So for here, the magnitude of magnetic field 1, we'll just write it as B1 for now, times the sine of the angle between the current in wire 2 and the magnetic field due to wire 1, dl. Now, the angle between the current in wire 1 and the magnetic field we already know is equal to 90 degrees, as we see from up here. Because it's 90 degrees, we know that the sine of 90 degrees is equal to 1. And since our current and magnetic field is constant, we could pull those outside of the integral, and we're left with the integral of dl. And when we integrate this, this is just the integral that is the product of the current in wire 2, the magnetic field due to wire 1, and the length of wire 2. And this is a familiar result, and a result that you should recognize, that for a current carrying wire in a uniform magnetic field, that current carrying wire experiences a magnetic force that is equal to the product of the current in the wire and the magnetic field the current is moving through and the length of the wire. So this is a great general result that you'll use time and again. Now, more generally, there should be a sine of the angle between the current and the magnetic field here, but in many circumstances you'll see that that angle is going to be 90 degrees. But just to be more inclusive, be sure you have this. Now for this problem, we have I2 BL, or the current in wire 2, the magnetic field of wire 1, and the length of wire 2. So working with that, the magnetic force on wire 2, the magnitude is given as the current in wire 2, the magnetic field due to wire 1, which is mu naught I1 over 2 pi times the distance between the two wires, L. Or we now have the result that the magnetic force on wire 2, its magnitude is given as mu naught over 2 pi r times the product of the two currents with the length of the wire. And if we were to do the same work to find the magnetic force on wire 1, we would see that the magnetic force on wire 1 is equal to the magnetic force on wire 2. And that's also told to us by Newton's third law. So here we have the magnitude of the magnetic force on each wire, and each wire will exert an attractive force on the other.